Alright, this lecture is going to be on reflection and refraction. That light rays change direction. Matter of fact, they have all kinds of different encounters. When we say light is going to travel from this media into a new media here, so we can say air and water, something happens at the boundary or the interface of the two. Some of the light is going to reflect. Some of it's going to be transmitted. Notice it's going to refract here at this boundary, which means it's going to bend. And then some of that energy is going to be absorbed. So we've got reflection, refraction, absorption, and transmitted. It's all taking place simultaneously. So here we go. So with reflection, when a wave reaches a boundary between two media, usually some or all the wave bounces back into the first medium. Some of the energy is transmitted or passes into the boundary or the medium which it collides with, while some is reflected back. So we did this with the slinkies. In the lab we completed with the slinkies, we saw waves reflect once they came into contact with a fixed or rigid boundary of our hands. They reflected back on the opposite side. So the waves start off on the one side and reflect back on the opposite side. But let's say we had another slinky or a piece of string. We had our original slinkies attached to something else. We would have actually seen the waves bounce back on the same side because this would not have been a rigid boundary. This would have only been partially reflected and partially transmitted. So it changes the circumstances. It changes the way the wave behaves. Well, we can apply this to how light reflects off of metallic and shiny surfaces. But not all surfaces are metallic or shiny. So a metallic surface is rigid to light and light waves that shine upon it. Light energy does not propagate into the metal, but instead is returned in a reflected wave. The wave reflected from the metal surface has almost the full intensity of the incident ray, the incoming wave, with the loss of only a small amount of energy lost due to friction of the vibrating electrons in the surface. So this is why metal, right, steel, silver, aluminum mirrors appear so shiny, because you cannot actually see its surface. So we call this here, with this mirror here, we're going to call this specular reflection. This is why this mirror works here, and this is why we can see a reflection in this steel ball here. It's really a concept of what is happening with the light reflecting off the surface. And if we take that even a step further, the light reflecting off the water or the metal object is polarized. Water and glass are not as rigid as metal. When light is shined onto still water, some of its energy is reflected back while the rest is transmitted. You actually get more sun when in water because of reflection of a water surface. So here if I say the photons are oscillating in all directions, right? So these pictures are the same here. That the reflected light is going to be polarized as it reflects. So reflection of light off a non-metallic surface results into some degree of polarization parallel to the surface. And that's what we see here. It's polarized light. So we can apply the concept of the law of reflection as we're talking about rays and light. So the surface generally we'll talk about mirrors. We'll talk about something reflecting or bouncing off. So the surface is what is reflecting the light or the photons. Could be a mirror, could be water, could be glass, could just be a wall. The rays, we'll talk about incident rays and reflected rays. The incoming rays are incident, the reflected rays are outgoing. The normal line is going to be a line that we're going to draw perpendicular to the surface, or to, in this case, the mirror. That's dashed, sometimes could be solid, line drawn perpendicular to the surface. We'll talk in angles. The angles are important here. We have an angle of incidence, right? That's the incoming angle measured from the normal line. And the angle of reflection. That's the outgoing angle measured from the normal. So I can see here that the angle of incidence is equal to my angle of reflection. The law of reflection states that the angle of incidence and the angle of reflection are equal to one another. So let's apply that here to plane mirrors. Plane mirrors here. One plane surface. Mirrors reflect light, but the image created is not exactly the image. It is actually switched left-right. So a plane mirror in the picture illustrates this. So why would the word ambulance be written backwards on the front of an automobile or on the front of an ambulance itself? Well, hopefully you can answer that question. So what is a plane mirror? Well, a plane mirror is the typical mirror that you're most likely used to. It's flat or planar. Plane mirrors produce only virtual images, meaning the image you're seeing isn't actually you. It's a virtual image of you. You're not emitting light. It's not light reflecting off of something. You're imposing those photons as they reflect off the surface. And we'll get more into this picture in a minute. Because you experience light traveling in straight lines, you see light rays reflected off a mirror surface directly into your eye. The virtual image is not an image that appears to be in a location where light does not really reach. Excuse me, a virtual image is an image that appears to be in a location where light does not actually reach. So your eye cannot tell the difference between an object and its virtual image, because the light that encounters your eye is entering in exactly the same manner as it would without the mirror if it were really there, if there really were an object behind. So you see yourself, well, you're not exactly this one, but you get the concept. Because light strikes off your shoes, reflects off the mirror, makes it to your eyes. You view it as if it's over here. So we'll do some imaging, we'll do some tracing of light rays as we continue moving forward here. So here we're going to move into refraction, right? Bending of light. So ponds or swimming pools appear shallower than they actually are. It's a function, a result of refraction. A pencil in a glass of water appears bent, and stars twinkle all as a result of refracting light. Changes in the speed of light as it passes from one medium to another, or variations in temperature and density, cause refraction, right? We have two different media. So what's happening is that light entering from air into water is going to refract. We have a new media. It's a different boundary, and they have different, let's just say, physical properties that lead to the refraction. So here we can start looking at n values. So the direction and the amount of bending depends on what is called the index of refraction, or n value. So if I look at this picture, I have light coming in here. It's going to refract as it goes into this, I think this is probably a plastic piece, and it's going to refract as it comes back out. So here's what's happening. Here's the rules we're going to follow, that a light path. We have to talk about, we need to know n values. We need to know their refractive indices. If it travels from high refractive index to a low refractive index, it's going to bend away from the normal line. Remember, the normal line is always perpendicular to the surface. And if it travels, if it's a low n value into a high n value, it's going to bend towards the normal line. So let's apply this concept to this picture. Let's say I have a light ray traveling from air, has an n value of 1.0001, and it travels into glass that has an n value of 1.5. It's going from a low n value into a high n value. It's going to refract or bend towards the normal line. So notice my angle of incidence here of my light ray coming in, my incident ray. When it refracts, it's going to actually refract towards the normal line. And that's what I see in this picture. It's got a smaller angle of refraction. And then as this photon or this light keeps on traveling in a straight line, it's going to go from from glass out into air, from a n value of 1.5 into an n value of 1.0001. It's going to go from high to low. It's going to bend away from the normal line. So notice my angle of incidence here is a smaller angle. It's going to refract or bend away. So my angle of refraction is going to bend away from the normal line. Remember, the normal line is always perpendicular to the surfaces. So we can apply the concept to this picture. So here we can see that light can have multiple interactions simultaneously. In the picture, we see incident rays striking the surface of water. 4 interactions occur. 1, some of the light is reflected. Boom, there's your reflection angle. Some of the light is transmitted. Boom, some of it passes through. Right? Remember, we're talking air and water here. Some of the energy of the light is absorbed into the water, right? It would change generally the heat or the temperature of the molecules in which it's being absorbed into. It would increase the kinetic energy. That's really what heat is. And number 4, the light is refracted as it travels from one substance into another substance with a different n value, or a different refractive index. So it's going to come in at one angle. It's going to refract as a result of traveling from air into water. They have different refractive indices. So last but never least, is the straw in water in both scenarios? Well, from our pictures before, from what we've done before, you'd see that, well, this one here is very likely water. Well, how do we know just by looking? Well, this is consistent with the picture I showed you with the refraction of in a prior picture. So we can apply that. But based on this picture right here, we have to say, well, this isn't water. This water is going to have the same refractive index anywhere and everywhere. In this case, this bends differently. So this is safe to say it's not water. So describe how the following terms apply. Reflection. Light from the surrounding area, surrounding this glass, I'll focus on the straw and water, are going to travel into the air, into the glass, into the liquid, the water, hit the straw. Some energy is going to be reflected, some is going to be absorbed. It's going to reflect back to our eyes. As it travels from the air into the glass, it's going to refract. As it travels from the glass into the water, it's going to refract. And the angle of refraction can be based on what the n values, or the refractive indices, are for all of the substances in which the light travels through. There you have it.